Okay, I'll be discussing a paper from last year, uh, written with Jiaqi Jiang, a former Princeton student, and Wenli Zhao, a current Princeton student. It's titled Central Charges, Elliptic General, and Bekenstein-Hawking Entropy in 2,2 ADS3 CFT2. And I'll also cite some results from this earlier paper from 2018, written with Jim Liu, Finn Larsen, both at University of Michigan, and Phil Sepiotowski, a former PhD student at University of Michigan. So there has been a revival of interest in ADS3CFT2 in the past few years, and there has been multiple components to this revival. Some of them are listed here. Perhaps the first or one of the first components of the revival has been discovery of new orbifold dualities. So the original ADS3CFT2 dualities of Maldacena had 4,4 supersymmetry. These more recent papers introduced orbifold geometries with reduced supersymmetry. Another component of this revival has been new developments in string theory on ADS3. And we heard yesterday a nice talk by Lorenz Eberhardt discussing one example along these lines. Yet another direction has been integrability breakthroughs. Only in the last year, there have been multiple papers opening new directions in studying holographic CFT2s and strings on ADS3 using integrability methods and spin chain techniques. There has been also interplay with higher dimensional ADS-CFD, especially in the context of black hole microstate counting. And perhaps the hottest of all has been this direction pursued by Maxfield, Turiachi, Witten, and others in the past few years, connecting ADS3CFT2 with lower dimensional holography, with near ADS2 near CFT1 in particular, and also with conformal bootstrap. I'm sure that there are others that I've forgotten, but I just wanted to make a point that there are multiple developments in ADS3CFT2, and there seems to be room for new projects and new follow-ups in most of these components. What I'll discuss today is a follow-up work to the papers that Eberhardt and collaborators wrote introducing new orbifold dualities in ADS3CFT2. So this is a paper from 2017 where Eberhardt introduced new 10-dimensional geometries that preserve 2,2 supersymmetry. There are G orbifolds of the standard 10-dimensional geometries that appear in Maldacena's original paper. Originally, we had ADS3 times S3 times either T4 or K3, and the dual CFD was a superconformal sigma model with target space infinite fold symmetric orbifold of M4, T4 or K3. That was the standard 4,4 duality. Eberhardt realized one can introduce G orbifolds on the two sides of the duality and get reduced supersymmetry, get 2,2. When M4 is K3, there's only one choice for G, which is Z2. And on this side, Z2 acting on K3 gives what is called the Enrichs surface. When M4 is T4, it turns out there are 7 different choices for G. And each of those is called a hyperelliptic surface. So we have one ES Enrichs surface duality. and 7 HS dualities, hyperelliptic surface dualities. Eberhard himself checked the duality, roughly speaking, at tree level in the bulk and in the large N limit. This infinity here is roughly speaking N in the large N limit. In particular, he matched the BPS spectrum, the supersymmetric spectrum of the two sides. We'll discuss developing the dualities further to the one loop level in the bulk and to the finite N limit, to the finite N regime on the boundary. We'll discuss two kinds of one loop effects in the bulk. One is quantum corrections to the Weil anomaly, which can be computed by evaluating one loop corrections of each Kaluza line multiplied in the bulk to the bulk effective action, and then summing over all the bulk KK modes. So the idea is we have 10-dimensional geometry, but we can Kaluza-Klein reduce on the 7-dimensional part and get infinitely many Kaluza-Klein modes on ADS3, which we can analyze using perturbative QFT techniques. Matching holographic Weil anomalies in this context has been initiated by Henningson and Skenderis in 1998, and they did it at tree level. So at tree level, it turns out we need bulk tree level action, and taking its variation with respect to the volume of ADS, or more precisely the regularized volume of ADS. This should match the Weil anomaly of the boundary, which is defined by taking the variation of the boundary free energy with respect to Weil scalings of the boundary metric. The result from the boundary we expect to be proportional to the central charge, with the coefficient proportional to a topological invariant, which in 2 dimension is just integrated Ricci scalar. Henningson and Skenderis demonstrated that taking the variation of the bulk tree level action, which is the Einstein-Hilbert action, with respect to the volume of ADS, one gets the leading central charge of the boundary in the large N limit. So now moving to the one loop level in the bulk and to the finite N regime on the boundary, we want to demonstrate that the variation of the one loop correction to the bulk effective action with respect to the bulk volume matches the subleading piece of the boundary central charge. So one loop effects in the bulk, subleading results on the boundary. The way this is computed, it's just a standard one loop determinant type calculation to obtain one loop corrections to the bulk effective action for each bulk Kaluza-Klein field. One then has to sum over the infinitely many Kaluza-Klein modes. That sum is divergent and needs regularization. We introduced a systematic and powerful regularization in this paper from 2018, which goes through the high temperature limit of the bulk superconformal index, or more precisely the bulk NS-NS elliptic genus in the single particle sector. I'm suppressing all the details. The end result of the bulk calculation is that in the ES case, the subleading central charge of the boundary should be 3 in order to match the bulk computation. And in the HS cases, it should be 0. So this is the bulk result that we want to reproduce from boundary calculations. recall that there was one ES duality and 7 HS dualities. One ES duality and 7 HS dualities. In that one case, the subleading central charge of the boundary we expect to be 3. And in those other 7 cases, we expect it to be 0. And note that matching these requires extending Eberhardt's original proposal to the finite n regime, because as long as this is infinity, we cannot read from it the subleading central charges. So we need to find the finite n analog of Eberhardt's proposal. So this is one type of one-loop effect in the bulk that one can consider. Another prominent type of one-loop effect arises when looking at quantum corrections to bulk black hole entropy. So in ADS3, we have BTZ black holes, and on these BTZ backgrounds, one can compute the spectrum and find the one-loop correction arising from every field on this background to the bulk effective action. We will focus on a robust piece of that one-loop correction, which is known as the logarithmic correction to black hole entropy. This is very robust, and it turns out in odd dimensions, in particular in 3 dimensions, which we are focusing on, it gets contributions only from the 0 modes in the background. So the calculation again involves some standard one-loop determinant computation, this time on BTZ background. And then one has to sum over the 0 modes on that background. Here the sum doesn't need regularization. This is just a sum over finitely many 0 modes. And there are well-known expressions due to Sen and others for the contribution of each 0 mode, and one just has to sum over them depending on the spectrum. One can easily extract this coefficient of the log correction, and we did this for the Andrik surface case in the paper from last year. And I'm just suppressing all the details and telling you the final result is -3. In this talk, I won't tell you how this -3 is matched with the boundary computations. The way to do it is to compute the boundary elliptic genus using the digraph Moore-Verlinde formula, and then asymptotically analyze it in the large n limit to extract this log A coefficient. But it can be done, and it can be shown that the result matches the bulk computation. So this matching I'm suppressing in this talk, but this matching is the one I would like to highlight and explain in the rest of the talk. So that's our goal for the remaining 10 to 15 minutes. Eberhardt gave us this duality at 3 level in the bulk, large n limit on the boundary. Now we have results at 1 loop level in the bulk, which require us to develop the boundary beyond the large n limit to find the boundary CFT at finite n in order to extract the dual observables and match them with these results. As I said, a similar matching can be done at the level of the log corrections to the entropy, but that I will not discuss in this talk. And this is the outline of the rest of the talk. I'll tell you what brain system underlies these nu 2,2 dualities. If you recall, usually any ADS CFD is obtained by considering some stack of branes and then taking the near horizon limit or some decoupling limit. That's how Maldacena obtained ADS-CFT dualities. In Eberhardt's discussion, the branes don't appear. But in order to develop the duality beyond tree level in the bulk, large and limit on the boundary, we will need the brane system. So we will discuss them. And then we will discuss the low energy sigma models governing the brane dynamics. Those sigma models will give us the finite n counterpart of Eberhardt's symmetric orbifolds. And once we have the finite n sigma models, we can read the central charges and we will see the subleading central charges matches. The subleading central charges match with our bulk prediction here. That will be the success story of today's talk. And then at the end, I'll discuss a mysterious charge constraint, which is the open end of this project. There seems to be a puzzle that we don't fully understand, and we're leaving for future research. Here's the brane system. We take the original D1, D5 system that Maldacena considered and introduce a G orbifold on the background. What was the original D1, D5 system? We had D1 branes wrapping R times S1. This R is the time direction. This S1 is the compactified 9th spatial dimension. A D1 brane wraps a two-dimensional manifold, and these D1s wrap this R times S1. The D5 branes have 4 more spatial directions, so they need to wrap a 4 manifold in the rest of the geometry. When G is trivial, and we are back in the standard 4,4 scenario that Maldacena introduced, those D5 branes wrap M4. When G is non-trivial, we can't separate this M4. So what we need to do is to look for a submanifold of this more complicated geometry. In algebraic geometry terminology, we want to look for a divisor, for a 4-dimensional divisor inside this 6 manifold. In the ES case, where G is Z2 and M4 is K3, there is a divisor at Z equal to 0. Z is the complex coordinate on the C plane. This Z2 acts on C by sending Z2 minus Z, so Z equal to 0 remains fixed. Therefore, at Z equal to 0, G acts only on M4, which is K3, or in other words, we have a K3 mod Z2, which is the Enrique surface sitting at Z equal to 0 here. We have an Enrique surface divisor at Z equal to 0. It's important that this divisor doesn't have moduli, meaning at any non-zero Z, the divisor is different. So this divisor can't move along the Z direction. It's fixed at Z equal to 0. Why at non-zero Z the divisor is K3? Because any non-zero Z here, G maps it to a different Z, maps it to minus Z. So the orbifold identifies 2 different points on this Z plane. And therefore it doesn't reduce the M4. M4 remains the same at any non-zero Z. What does this imply for our brane system? It implies that if we have a single D5 brane wrapped on this M4 mod G divisor at z equal to 0, that brane would be stuck at z equal to 0. That brane won't be able to move along the z direction. And that's good news because for 2,2 dualities that we are interested in, supersymmetry countings show that we need two-dimensional Coulomb branches, which arises the brane moduli here when we consider the brane motion along this R2. So the fact that extra moduli don't arise from the C is a desirable feature. Note, however, that if we have pairs of D5 branes, if we have two D5 branes wrapped around this M4 mod G divisor, then they can combine. Then they can combine and move to non-zero Z, because two of these K3 mod Z2s then can unwrap themselves around K3. An interesting implication is that if we have an odd number of D5 branes and somehow they're bound together, for instance, by turning on a B field in supergravity or string theory, then they will be stuck at z equal to 0 and we get the desired number of moduli arising from motion on R2. But if we have an even number of D5 branes, even if they're bound together via a B field, for instance, they can combine and unwrap the divisor and move away and lead to extra moduli. And this supremacy of odd number of D5 branes will appear again in this talk shortly, as we'll see. So that's the brane system, and this is the subtlety with the number of D5 branes in the system. In ADS3CFT2 context, what we do with this brane system is we focus on its near horizon geometry, and a very similar argument to the standard argument that Maldacena gave in his original paper implies that the near horizon geometry here is ADS3 times this orbifolded 7-manifold. Therefore, we get Eberhardt's geometry by focusing on the near horizon limit of this brane system. But we get more because then we can look at the lower G sigma model of this brane system, and from the sigma model read the central charge in the finite end regime. How does this work? There's a formula for the dimension of the moduli space of D1 branes inside D5 branes. Roughly speaking, the D1s are thought of as instantons in D5 brane world volume, and there are formulas for the dimension of instanton moduli spaces that Vafa and collaborators have used successfully in this context since 95. This is the formula. K1 is the number of D1 branes, K5 is the number of D5 branes. Chi and tau are the Euler characteristic and the signature of this 4-manifold that the D5s are wrapping. In our context, M4 mod G. I have different notation for the number of D1 and D5 branes because while the number of D5 branes coincides with the D5 charge of the system denoted Q5, due to a very interesting anomalous I-brane inflow of D1 charge from the D5s, the D1 charge of the system is not K1, it's not the number of D1 branes. It's the number of D1 branes K1 plus some anomalous correction arising from the non-trivial topology of the D5s. In the ES case, this formula reads Q1 equals the number of D1 branes minus the number of D5 branes divided by 2. Combining these two formulas with the observation that the central charge of a sigma model is 3/2 its dimension of the target space gives this formula 6q1 q5 plus 3 for the central charge of the low energy sigma model in the ES case. What is this formula? This 3/2 times dimension of the target space arises because we have supersymmetric sigma models. So we have a boson for every dimension and a fermion. The boson has central charge 1, the fermion has central charge 1/2. We sum them, we get 3/2. So if we had a bosonic sigma model, dim of M would be the central charge. But because it's supersymmetric, each of those bosonic directions is accompanied by a fermionic superpartner, and we get 3/2 that dimension. This is our central charge, and I've put a check mark here because this subleading piece in the large N limit. Large N limit means sending Q1 and Q5 to infinity. The subleading piece comes out 3, which matches this whole computation. And that's our success story for today. A similar computation can be done for the HS cases, and we get 0. And again, we have a successful match with the earlier results from the bulk. With this central charge, we can then find the finite n symmetric orbifold that should replace Eberhardt's infinite fold symmetric orbifold. And that finite n version is this. Why this? Because ES has 4 dimensions. 3/2 4 gives 6. So 6 would be the central charge of a single copy, and we need these many copies so that once they're multiplied by 6, we get this formula. So that's our success story. Let me end with this mysterious charge constraint, which is a bit of an open end of our work. We see in the ES case that to have Q1, Q5 plus 1/2, an integer, which we should have, otherwise a symmetric orbifold doesn't make sense. Recall that symmetric orbifold means multiplying this many Undrich surfaces and then taking the symmetric quotient, identifying under permutations. So this number should be a well-defined integer, otherwise we can't form the product. For this to be an integer, Q5 should be odd, because if Q5 is odd, K1 minus Q5 over 2 would be half integer, Q1 times Q5 would be half integer, and the sum would be integer. So then things would work. But can we understand this odd Q5 constraint from the brane perspective? We saw earlier that odd Q5 was...
interrupting you. I don't know, maybe you can sum it up in 2 minutes. Is it possible?
Sure. 30 seconds, I'll be done.
Okay.
Thanks for the reminder.
Okay, thank you. I wrote the reminders, but maybe you didn't.
Yes, I didn't see it. Appreciate it. Yeah, so we saw that we appreciated having Q5 being odd, but that's not quite a proof, because in principle, one can have the extra moduli decouple. So while we don't have a proof, we have some indication from the brane system that Q5 better be an odd number. From the bulk ADS3 perspective, there is another argument due to Data-Eberhard-Gabardiel that space-time supersymmetry in the twisted sector necessitates odd Q5. So from various perspectives, one can see this Q5 in some perspectives more strongly, but in some perspectives not as strongly. And in fact, the bad news is in the HS cases, similar constraints arise, and in different perspectives, they seem to be different, and we don't really fully understand what's going on there. That ends my talk. Thanks very much for your attention, and this is the short summary that we had successful CFD matching of bulk one-loop effects, in particular circulating central charge and the law correction to the black hole entropy, but there are these mysterious charge constraints that we don't fully understand. Thanks a lot.
Yeah, thanks, Arash, for your nice talk. And we have time for one short question, if any. Maybe I hear Mr. Jafari or Miss Jafari, maybe you wanted to ask a question. Yeah. Yes. You have access to your mic, Ms. Jafari. You can ask your question.
Yeah. Hello.
Hello.
Nice seminar and nice talk with Arash.
Thank you.
Elementary question.
Please.
Yeah, I have doubt about the Lorentz invariance in extra dimensions. If you go to dimensions more than 4, in any books in supergravity, supersymmetry, you have assumption that Lorentz invariance is not violated. You have Lorentz invariance. Is it assumption a good assumption? Is there any experiment or any evidence for testing this?
So the way I understand it in this context is there is a local Lorentz invariance in the sense that the metric has Lorentz signature. And that seems to be compatible with the experiment as far as I know. But there is another sense that Lorentz invariance can arise in some situations, and that's when we have asymptotically flat spacetimes. Then Lorentz symmetry arises as the asymptotic symmetry group, or as the isometry group of our manifold, of our spacetime manifold. That Lorentz symmetry, of course, doesn't exist here, because our isometry group here is isomorphic to the conformal group, not the Lorentz group. Is isomorphic to the two-dimensional conformal group. And the isometry here is a complicated, maybe SU2 or something like that. So that's my comment.
Yeah, thanks, Arash. And I use this opportunity to ask my very quick question. My question is there any way to make a relationship between the lattice field theory entropy and also the Bekenstein-Hawking entropy to overcome the difficulties which appears in 4 dimensions 1 plus 3? We have a lot of degrees of freedom in such system. Is there any way to make any constraint to overcome this problem?
I haven't thought about it. It's an interesting question, how one can use lattice field theory to get insights into entropy. I haven't thought about it, but I will think about it. I'll write to you.
Okay, thank you so much. Thank you, Arash.
Sure.
Thank you so much. Again,